Wine. I'm curious.
That's what I thought.
Sounds good.
But I have to say, teaching this class is very different from teaching whatever general chemistry or
All right.
even PChem. Very
What's-
quite different.
What's
So,
the-
much more laid back. I mean, you have to just take it slow, give yourself time to think, otherwise you just doesn't work.
No formal.
Oh, okay.
So sometime yesterday, I put up the homework, the next homework. Oh, I emailed you that,
I
right?
like that email. Great news! Wonderful news!
Exciting.
Was it exciting news? Was it?
No, great news.
So, but actually, this should be sort of get into this chapter. What is this, 5 or 6? Or something? 5.
Well, delightful news.
It should be
It was delightful.
delightful. Yeah, this should be nice, or a little fulfilling because we've developed this approach for determining our bulk properties on the basis of a partition function. We sort of seen how to express all the thermodynamic quantities in terms of a partition function, this ensemble, that ensemble, whatever ensemble we find convenient. And then we spend a chapter saying, okay, we probably can't calculate quantum mechanically directly the energy levels of the whole system, but we related the partition function for the system to a partition function for an individual molecule. And the number of molecules got in there, and we saw that even if they're fermion, regardless of whether these particles are fermions or bosons, if the temperature is high enough, then we get a pretty simple formula for the partition function for the system in terms of a partition function for the individual molecule, and it was just that. That, of course, is Boltzmann statistics, and we know that it has its limits at low temperature. Then you have to think about, am I a fermion or a boson, and you get a more complicated formula. But really, for most of this class, we'll assume where Boltzmann statistics applies, that it's reasonably accurate for our purposes. So with that, then, in this chapter, we're going to apply our formalism to an ideal gas, a monatomic gas. So this is pretty simple. We're assuming there are no intermolecular interactions. We're at a high enough temperature the Boltzmann statistics is reasonably accurate. There's no rotation to think about. There's no vibration to think about because we're monatomic. What can we see? So we're going to apply Boltzmann statistics now to a monatomic, ideal or perfect gas. So that's all we're going to do in this chapter. So what we need then to begin with, of course, is Q, which is the sum over all the states. So we need an expression for epsilon. And for our purposes, we're going to think of a box, because we know we can solve the Schrödinger's equation for a particle in a box. And for simplicity, I'm going to assume this is a cube. So the 3 sides are all the same. We'll call them A. One of the homework problems extends this to a box with different side lengths, and you see the results exactly the same. We're just going to assume a cube for simplicity. So we know then that the energy of the system is that where n, x, n, y, and nz are three quantum numbers, each going from 1 up to as large as you want to get, but the smallest number is 1. And that's that. So what we're going to do is plug this expression for the energy in to our expression for little q and then big Q, and then we'll insert that into the expressions for the Helmholtz energy or the entropy or the energy, the internal energy, and see what we get. And I mean, of course, we'll end up with this, the ideal gas equation and some familiar equations, but no longer are they pulled out of a hat. You can see how they come very simply, straightforwardly from our statistical mechanical approach. Yeah, so let's go ahead. It's worthwhile doing a little math because it takes us somewhere where we feel like we're on firm ground. So we just want to substitute this in here, realizing that we're summing over 3 indices. So this becomes which becomes now that's only part of it. That's just the nx squared part. But from this, you can see that the other, the ny and nz, will give you 2 more sums of exactly the same form. And they'll both be running, the index will run from 1 to infinity. So the sums will have to be the same. So you might as well just deal with this one and realize it gets cubed. Right. So that's all there is to that. And I guess I jumped ahead. Man, I jumped ahead. Let me backtrack, because I kind of left something out. Here I am backtracking. What's Q? Well, for our monatomic gas, we have 3 things to think about. We have overall translation. The atom may have electronic energy levels, and the nucleus may have nuclear energy levels. So we have to think about all of these things. So we can generally factor Q into a translational part, an electronic part, and a nuclear part. Now, if this were a polyatomic gas, we'd also have rotation and vibration to consider, but now this is all we got. Right now, what I'm doing with parking lot of box, I'm thinking only about the translational part, and we'll deal with the others later. So this right here is really the translational part of Q, not the full Q. I jumped ahead. So we'll deal with these 3 things one at a time. You remember we showed that when the Hamiltonian is separable into a term for translation and a term for electron and a term for nuclei, when the Hamiltonian is separable, then the partition function becomes product. We saw that last chapter. And to a very good approximation, translation, electronic energy, and the nuclear energy are separable. So that's why this is pretty good. But we'll see later, in fact, that the most important part of this product is the translational part, to the magnitude. So that's that. We'd like a simpler expression. Translational states are very, very closely spaced in energy. You don't really even detect the discrete nature of translation. It's essentially continuous. So since it's a continuous, we can approximate this with an integral. So, for example, let this be n sub x, which takes on discrete numbers, and for a particular value of n sub x, this exponential has some value. So if x is 1, it has this value. If x is 2, it has this value. If x is 3, it has this value. So I can approximate this, of course, as an integral. That's what we'll do. So this becomes, and you can let the index run from 0 to infinity. I dropped the subscript on the n, and you just have to evaluate this. Remember that, look up in a table. Let's see. Can't write this legibly here. So I'll just quote the results. Let's just take this part right here. That. So the whole thing then becomes we usually write this way. So when you carry out this integral, you can do it slowly if you want. This is what you get. Of course, there's a square root. And then when you have 3 of these together, you get the 3/2. A is the length of the box, so a cubed is just a volume, so we write it as V. Now, it's common nomenclature to define something called a capital lambda as this, so that we can write it that way. Okay, so I'll say more about capital lambda in a second. Right now, I'm just going to make the point that its units, if you work it out, happen to be units of length. So when you cube it, you get units of volume, and the partition function is unitless as you'd expect. You can convince yourself of that, I think. Okay. Now, first I want to think about the energy for a second, now that we have this expression. And we'll find a not surprising result. Suppose we're interested in the energy of a particular particle. And what I want is the average energy that's translational for this particle. Of course, the average energy is minus the partial of q with respect to beta, right? Or if we q, log q. Or we could convert from beta to t. And let's see, what is that going to give us? Well, let's rewrite, here's the q, right? It's right here. Let's think about this for a second. If we're taking the log of q, of course the log of the product is the sum of the logs, right? And we're taking a partial derivative with respect to t. So all that matters here is the log of t to the 3/2. Right? This can be written as the log of q translational can be the log of 2 pi mk over h squared to the 3/2 times v plus the log of t to the 3/2. And when you take this partial derivative, everything except the log of t to the 3/2 just drops out, right? Just 0. So this becomes which obviously is just going to give you 3/2 kT, right? And in this case, the average energy of the system is just going to be equal to n times the average, and we're talking translational, times the average for some particular particle, so that will be 3/2 n kT. Or if you're talking about Avogadro's number, RT, which maybe says, oh my God, that's amazing, how can that be? Wow, cool. You realize it really didn't, this could have been anything. As long as this was t to the 3/2, it's always going to be that result. Right? So it's not quite as amazing. It's kind of cool, but okay. So with that result now, I want to go back to lambda and think about an interpretation of lambda. And think about it this way. Translational energy is 1/2 mv squared, right? Its kinetic energy is 1/2 mv squared, which you can also write as p squared over 2m, where p is the momentum. So that P is this. Right. Now I'm being a little bit cavalier here because what I want to do is, but what I want to do now is substitute for E translational 3/2 kT. So that's the momentum. Now I've been a little bit cavalier because technically that's the average translational energy, so apparently that's equal to the average of p squared divided by 2m, and that's still there, and this is really the root mean square. But right now, as you'll see, I'm not so concerned about the difference between the average speed of the root mean square speed, or the average momentum of the root mean square, or the root mean square momentum. Not so concerned with that. I want to make a connection. Do you remember back to...
What are you concerned about?
Huh?
No, what are you concerned about?
I'll show you in a second.
Okay.
Do you remember in early quantum mechanics we said any particle also has a wavelength? You can associate with any particle a wavelength. We called it, anybody remember what we called it? That wavelength? de Broglie. So we said that there's a wavelength. If you think of a particle and it has some momentum p, then you can also ascribe to the particle a wavelength lambda, and we call that the de Broglie wavelength. Or de Broglie, it looks like. De Broglie, something like that. So this is the de Broglie wavelength. Okay. So notice that, let's put it this way, h over, if we really want to be careful here, h divided by the root mean square momentum, we really want to be careful, which is in quantum mechanics, we usually show that the root mean square momentum and the average momentum are similar within a factor of 2. And right now I'm just talking about what's a factor of 2 among friends, sort of physics sort of thing. This is what I'm getting at. Okay. Now, So I just wrote this h over p as the square root of h squared over 3 mkt, right? Okay, that's cool. And now look at this, and look at this. Okay, they're not exactly the same thing, but the h squared and the mkt are the same. And here we have, and the 1 to the power of 1/2, here's a 3 and here's a 2 pi. So 2 pi is whatever, 6 point something. So this is actually better than a factor of 2 among friends. This is a factor of the square root of 2 among friends, right? So this thing that we call lambda is kind of like, very similar to the de Broglie wavelength of the average particle under thermal excitation. So your average particle has a particular momentum. We're actually talking about the root mean square momentum. And we can see that the particle that happens to have the root mean square momentum will have a de Broglie wavelength of this value, right? It's not exactly the same thing as this, but it is to within less than a factor of 2. Okay. And this is a quantity that comes right out of the partition function business. So we give this a name. It's convention to give it a name and call it the thermal de Broglie wavelength. And now you can ask yourself, okay, when is this approach appropriate? In other words, when is Boltzmann's statistics applicable? And the answer kind of is, it's applicable when the thermal de Broglie wavelength is much, much smaller than the volume of than the length of your box.
Lambda is a thermal de Broglie wavelength.
Sorry?
There's a lambda. That's the thermal de Broglie wavelength.
The capital lambda is the thermal de Broglie wavelength. So when the box size is much larger than the thermal de Broglie wavelength, then Boltzmann's statistics can be used. Or, in other words, or when the ratio of the thermal de Broglie wavelength cubed to the volume is much less than 1, then Boltzmann statistics is generally applicable. That's the point. So I think I've said all I need to say about the translational part. Any questions? So this is a very famous quantity. This is a very famous quantity right here. You'll see that 2 pi mk, well, the thermal de Broglie wavelength will appear very frequently because, even larger molecules, diatomics and polyatomics all have overall translational motion, so that'll keep popping up. So cool, then we can go on to the electronic and the nuclear parts. Actually, I could have left that.
Are you current, Scribe?
You know what, I don't think it is though.
It's returning the same level of treatment. I wish I had the book for the day that I asked that question in PChem 2, and I said the Broglie, the face on Chatfield's face.
And you remember to this day, man.
I still remember that. You're very key on the pronunciations.
I don't know, that's just a little thing I got.
You should know that.
So now I want to think about the electronic part, which is a lot easier to deal with because electronic states are usually pretty widely spaced compared to translational states. So, so the Q electronic is a sum over states, but we usually change it to sum over levels and include a degeneracy factor. That's the usual thing. So, I'll let I represent levels. Here J was degeneracy, so this is going to be some degeneracy. I'm using the book's notation. So for degeneracy, I'm using the symbol omega. That's the lowercase omega. Before we used the uppercase for degeneracy, which is that looks like a horseshoe or something. But now we're using the lowercase omega, big deal. And we're using an E for electronic as a subscript and so forth. So this becomes, you just write it out. That's good. So convention is to set epsilon for the lowest energy level equal to 0. Your zero of energy is set arbitrarily in general, so the exponential becomes 1. Generally, the electronic states are spaced apart from each other by enough energy that, for most purposes, you need at most the first excited state. And the degeneracies, usually that's enough. Depends. If you open your book, it's worth opening the book and just looking at a page.
What are you doing here?
That'd be page 84. They've got a bunch of atoms, and the different states for the different atoms. And if you remember back to PChem, well, you guys are used to this. Certainly Alex Landera is from all your work. of course, there are the electron configurations, and then there's the term symbol. We know that the electron configuration doesn't fully specify a state. You need to specify more stuff. The orbital angular momentum and the spin angular momentum and the total angular momentum are given in the term symbol. I'm not going to go over term symbols in this course because that's really a separate topic, but we do make reference to it. And at the very end of the chapter, they very quickly summarize what's behind term symbols. But it's not really enough to understand well. You kind of need to go back to quantum mechanics. Degeneracies are given, and the energies in reciprocal centimeters and in electron volts. So the whole point there is that, well, for hydrogen, the first excited state is 10 eV above the ground state. And if you do a little math, you're going to see that that makes this pretty much negligible for most circumstances compared to this. And helium is even more. Lithium, that's okay, 2. Oxygen gets a bit closer, and then you find for the halogens that the first excited state is quite close to the ground state. So sometimes for halogens this may be important. This first term here, depending, but the subsequent ones even then, you can see the second excited state for the halogen is like a 13. So for our purposes, we're just going to worry about the ground state degeneracy and maybe the first excited state degeneracy and energy. And if you need more, you can do more. They spend some time in the chapter talking about the fractional populations of the various states. Easy to get at. You know, so that's the electronic wave function. And the nuclear wave function same idea. Generally, the first excited nuclear state is well above the ground nuclear state, so we neglect even that. So for the nucleus, our approximation for Q our approximation is this. This is approximate, but it's often good enough. And in fact, we're going to omit this. We usually omit this. The reason we omit it is that in chemistry, we're mainly interested in change. What's the difference? What's delta S between two states? Or what's delta U or delta H or delta G, you know? And the nuclear wave function rarely changes. So when you take the delta, the difference, it's going to disappear, cancel out. So we're not going to worry about it. Okay. So generally, this is all you need to worry about.
I never thought of excited nuclear state.
Sorry?
I never thought of excited nuclear state.
Yeah, well, they exist. That's NMR is all about that. Nuclear spin flips and so forth.
I have a question for you. And I'm probably jumping the gun a little bit this for monotonic gas, but last class we decided to look up the difference between bosons and fermions to review. And when you talk about protons, you know, they're fermions, but they said if you can have like if your nucleus has, you know, a proton and a neutron, then you can treat it as a boson. You always treat the nucleus as a sum of the parts.
So,
I guess eventually the point's gonna come where we have to treat these as either fermions or bosons.
yeah, if you're very cold, you're gonna have to think about whether your nucleus is a fermion or a boson.
Oh, but only when it's very cold.
Well, no, I guess that's not really true. From the point of view of chemistry, it's not gonna matter because it's not gonna change.
Okay.
From the point of view of, on very high temperature, maybe you have to start to think about it. But at very cold temperature, it's just not going to be important to us as chemists. As physicists, it may well be. So, so that's that. So with that, kind of the last thing I want to do is to plug in our expressions for the partition function for a monatomic gas, monatomic ideal gas, into the expressions for a couple of thermodynamic quantities to see what we get. Since we've been dealing in terms of the canonical partition function for convenience, I'll stick with that. Right, that's our expression for A, right? So you can simply plug in. This is log Q. Of course, Q we saw was, I want to write it out now. Right within our approximation, that is little q, and so if we want big Q, that's what we get. I usually, it's a usual thing. Notice that we have the product of terms in the numerator, all to the n, and the n prime in the denominator. It's usual to think about the n prime together with the translational part, just for convenience, so it's really arbitrary. So this becomes actually, I'm just going to write the result down because there's no reason to doing a lot of math. You'll see this in the book. So you'll see that in the book, and let me just explain a couple things look mysterious. But remember, because of this in the logarithm, we have an n log n minus n term, right? And so, for convenience, for some reason, the book likes to combine this, and note that you can write this as n log n minus log minus n log e, the logarithm of e being 1. So this becomes and when this gets subtracted, it becomes this part right here. And I left off a logarithm. So that e over n part comes from this. That's all. And so e is the number 2 points. It's not the charge of